Greetings. So, with today's class and the next one we will be concluding the unit 7 basically on photoionization cross section, and we will also get expression for the angular distribution of photoelectrons. And we found that the differential cross section which is the cross section per unit solid angle for a given direction of incidence with respect to which you describe this geometry, and if you have the incident electromagnetic radiation having electric vector polarized along the unit vector epsilon, and you set it up along this x axis. For our consideration, kf is the unit vector along the photoelectron momentum as it escapes the atom. Then you express it in terms of this matrix element modulus squared, and essentially this is coming from the time dependent perturbation theory and an application of the Fermi's golden rule as we discussed in our previous class. We also found that the differential cross section has got the dimensions of L square. It is usually measured in units of megabarn, which is 10 to the minus 18 centimeter, and then if you integrate it over various directions of polarizations and all the polar angles, then we find that the cross section certainly drops as the energy increases. So, the rate at which it drops with energy is e to the minus 7 by 2. So, obviously the photoionization cross section is maximum at the threshold, at the photoionization threshold, okay, that is when the photoelectron energy will be roughly 0. So, right at the threshold you expect the photoionization cross section to be maximum, and then it would fall monotonically, okay, according to this power law, which is e to the power minus 7 by 2. Now, of course, a number of approximations have gone into this, the Born approximation, and there are several other considerations, as a result of which there is a departure from this e to the minus 7 by 2. Also the fact that the cross section is not always decreasing monotonically, it can go down and go up, and there are these additional considerations that one really has to talk about. It also goes as the fifth power of z and as n to the minus 3, where n is the principal quantum number. So, we will have a closer look at this matrix element which goes into the photoionization cross section, and this matrix element is the matrix element of the gradient operator. So, you write it in terms of the momentum operator. So, you get a factor of I over h cross outside, and you have got the momentum operator inside the matrix element, and here you have got e to the I k dot r, which you can expand as a power series in r over lambda, okay. K dot r is k r cos theta, k is 2 pi over lambda. So, e to the I k dot r is actually a power series. So, if you take the leading term, you have e to the I k dot r nearly equal to 1, which is called as the dipole approximation, and I will explain why it is called as a dipole approximation. So, tentatively we will use the term dipole approximation, and very quickly we will recognize why it is called as a dipole approximation. And this will work for low energies, for large wavelengths, and this will work for low energies which are not all that low. This works all the way up to about 5 or 6,000 electron volts above the ionization threshold, although there are some exceptions and one has to make corrections for them. And if you now set this e to the I k dot r equal to 1, then you have an equality in this approximation in which you no longer have to write the e to the I k dot r explicitly, because it has been approximated to unity, okay, that is set equal to 1. So, the last expression that you see over here is appropriate within the dipole approximation, although one has to go beyond the dipole approximation, but that is a matter of detail. So, now we have an expression for the dipole approximation for this matrix element, which enters our expression for the differential cross section, and although we find that this is the matrix element of the momentum operator, and the momentum being proportional to velocity, this form of the matrix element is sometimes called as the momentum form or also as the velocity form. Okay. But you can also write it in another form which is known as the position form or the length form, and the reason you can do it is because the position operator and the momentum operator, these two operators have got well known commutation relations. Okay. So you can convert from one to the other, and this is the commutation between r and p square. The reason I am considering the commutation between r and p square is because in the Hamiltonian you have got the potential energy operator which depends on r, and you have got the kinetic energy operator which depends on p square, right. So if you consider the commutation between r and p square, you find using basic commutation relation that this is equal to twice I h cross p for each component k going from 1 to 3 for x, y, z, and that tells us that the Hamiltonian would have a commutation relation with the position operator which is given by the commutation of r with the kinetic energy operator. It will of course commute with the position with the potential energy operator which depends on r alone, right. So it would commute with the potential energy operator, and the commutation with p square would give us I h cross over m p k for the kth component. So this matrix element, which is the matrix element of p k, right. So this is the matrix element of the kth component of the momentum operator. So this can be written in terms of the matrix element of the commutator of the position operator and the Hamiltonian scaled by this m over I h cross which is coming from here, right. So you can write the matrix element in terms of the matrix element of the momentum operator, or effectively in terms of the commutator x with h 0, and now you take the x h 0 commutator explicitly which is x h 0 minus h 0 x. So you will get two terms on the right hand side, but then I and f are both eigenstates of the unperturbed Hamiltonian h 0. So when h 0 operates on f, you will get E f times f, and when h 0 operates on I, and it would operate on either side, it is a Hermitian operator, so you will get E I times the state vector I, and using this you find that this matrix element is equal to, this is m over h cross square, and you get E I minus E f, and you have this matrix element, right. So the matrix element of the momentum operator, this is the quantity which we want to evaluate, but equivalently we can also evaluate this matrix element which is the matrix element of the position operator rather than the momentum operator. The difference is that when you have the momentum operator, you will have to take the derivative of the function on which it is operating and then carry out the integration, whereas for the position operator you will only multiply it out because both of these are space integrals. Okay, but when getting the space integral, in one case you will have to take the derivative of the function on which it is operating, so which is what you will have to do in the momentum operator, and in either case you must get the same result because there is a complete equivalence between the matrix element of the momentum operator with the matrix element of the position operator. All you have to do is to multiply by this I m times the frequency of transition. This is the circular frequency because you get the energy over h cross. Okay. Now this is, these two forms of the matrix elements are called as the momentum form and the length form of the matrix element, and it's a matter of great pride with which I like to report this particular thing, because the different forms of the matrix elements, the length form, the momentum form, and in fact there is a third form also which is known as the acceleration form, and this analysis was done by Chandrasekhar, and this is reported in the Astrophysical Journal volume 102, and this is a very beautiful paper by S. Chandrasekhar He is of course known, very well known for a lot of excellent work in astrophysics, but this is also at, this goes back to Chandrasekhar and his contributions to spectroscopy. So you will nevertheless need to recall a discussion from unit 4 on Hartree-Fock, because whereas for the hydrogen atom the length form and the momentum form will give you the exact identity, it does not matter which form you are using. For a real atom, when you extend this analysis for many electron systems and you carry forward the formulation from single electron atoms to many electron atoms and use the same kind of formulation, you have to take account of the fact that in a real atom there are a large number of electrons, and the Coulomb interaction between them is what needs to be handled correctly. And when you take into account the Coulomb interaction and also the antisymmetry of the wave function, you are led to the Hartree-Fock equation, and this is the Hartree-Fock equation that we discussed in the unit 4. And let me remind you that there are two potentials over here. One is the direct potential, in which Q gets integrated out. So this potential, the direct potential, is then it depends only on the coordinate q1, but the exchange potential is a global potential, because here if you integrate 2, you have to keep track of the fact that this is ui and this is uj. So you really need to solve this equation for all the n electrons. So this is the potential which is a global potential, it is not a local potential. And since this is not a local potential, you have the Hartree-Fock potential, which is a sum of these two terms, the direct potential and the exchange potential. But the exchange potential makes the Hartree-Fock equation looks very similar to an eigenvalue equation, but as we discussed in unit 4, it is a deceptively simple form, it is not an eigenvalue equation, and the reason it is not an eigenvalue equation is because of the non-local potential. Now what is the consequence of the non-local potential in the present context? The non-local potential will cause a breakdown of the equivalence between the momentum form and the length form of the matrix element, because the equivalence between these two forms, that you just have a multiplier I m omega, and this is the only thing which connects. If you just multiply the length form by this factor I m omega, you should get the momentum form. This thing assumes that the position operator commutes with the potential energy operator, okay? And the potential energy operator, if it is non-local, it does not depend just on the argument r, but it also depends on r prime. So the position operator will not then commute with the non-local potential, and you will not then get an equivalence between the length form and the momentum form of the matrix element. So you will, when you do the calculation, you will get one result if you use the length form, you will get another result if you use the velocity form. So these are certain details. The other thing that I mentioned is that if you just look at this e to the minus 7 by 2 law, you get a feeling as if the cross section, the photoionization cross section will have a certain maximum value at the threshold, and from there on it will only fall monotonically according to e to the minus 7 by 2. So there may be, you will expect that okay, there will be some corrections, it may not be strictly e to the minus 7 by 2, but at least qualitatively it will always decrease with energy. Now even qualitatively this does not happen necessarily in all cases, even in the single particle approximation, and the reason it does not happen is because the cross section, it falls, goes through a local minimum, rises again and then falls. So this local minimum is what is called as a Cooper minimum, and the reason it happens is because of a very simple reason which I will mention in brief, that if you look at photoionization of the neon atom, now neon has got 10 electrons, so you have 1s2, 2s2, 2p6. So 2p is the outer shell of neon, and you consider the photoionization of the 2p electrons from the neon atom, which are being knocked out into the continuum by absorption of electromagnetic energy. So now let us have a look at the 2p wave function. the 2p wave function, if you look at the matrix element of the position operator, all you have done is to sandwich the position operator between the initial state, which is 2p, and the final state, which is a continuum what? It is a continuum p to d transition. So let us consider dipole transitions from 2p to d. There can also be a transition from 2p to s, but the dominant contribution comes from 2p to d. So we will consider the 2p to d transition, and this is the d continuum wave, and to get a non-zero matrix element over here, this is the matrix element which is contributing to the photoionization cross section. This matrix element is coming from the overlap of the 2p wave function with the continuum d, right. Now if you consider, instead of neon, just the next atom in the periodic table just below neon, okay, which is argon, which is a very similar atom, okay, its chemical properties are very similar, both are inert gas atoms, but then there is a significant difference in the nature of the wave function of the outer 2p wave function for neon and the outer 3p wave function for argon. What is the difference? 3p has got one node. The number of nodes a radial function has, as we studied earlier, is n minus l minus 1, right. So for n equal to 2, 2p is nodeless, but for n equal to 3, 3p has got one node. So here you see that 3p goes through a node, and now if you look at the overlap between the continuum d state and the initial state, for neon it is positive, whereas for argon this overlap is negative, okay. And then as the energy increases, the continuum d states will go more and more into the core, right, and then all there will be more oscillations of the continuum d state in the inner region, and at a certain point the positive contributions of the overlap and the negative contributions of the overlap will actually cancel, and from this negative later on you can also get a positive sign of the matrix element. So the sign of the matrix element of the position operator will actually change as a function of energy in the case of argon, but that is not going to happen in the case of neon. So what does it do to the matrix element? Matrix element actually undergoes a change in sign, and when it undergoes a change in sign, it will go through a 0, and when it goes through a 0, the matrix element is 0, there will be no photoionization. So the cross section will actually go to a 0, but then as the energy increases, again the oscillator strength will build up. Now this is what is called as a Cooper minimum. It is not always a strict 0, but that is again a matter of detail, because you can have transitions into various channels, not just 2p to d, but you also have transitions 2p to s. Then again 2p is not a single state, you have 2p 3/2 and 2p 1/2, and then from 2p 3/2 you do not have transitions to a single d state, you have transitions to two different d states. So you will have a transition from 2p 3/2 to d 5/2, 2p 3/2 to d 3/2, and these are the different channels in which photoionization will take place, and the Cooper minimum in each channel will not be necessarily at the same energy. So the cross section itself will not be necessarily 0, but it will certainly be a minimum, and this is what is called as a Cooper minimum. So this is a picture of the matrix element. For neon it is positive, and then eventually it goes to 0 as the electron energy or the photoelectron energy increases. In the case of argon and krypton also, certainly the matrix element eventually goes to 0 at high energies, but then it starts out as negative, goes through a 0, cuts the 0 line over here, turns positive, and then goes to 0. So argon and krypton will have a Cooper minimum, but not neon. So here is an example of a Cooper minimum in which you see that the photoionization cross section, this is a calculation of the mercury 6s, you see that the photoionization cross section has dropped, it goes through a minimum and then it rises again. So it is not always a monotonically decreasing function of energy. So this is what we have found so far, and it is coming because we are looking at the matrix element in the dipole approximation, in which we considered the length and velocity or length and momentum forms of the matrix element. So this is the expression for the matrix element, and I have written a superscript d for the dipole approximation, which is what we have got. But if you take the next term over here, okay, so e to the ik dot r, if you take the next term, you will then get corrections to the dipole approximation, and then you will get higher multipole. So from dipole you will go to quadrupole and so on. So you have a Cooper minimum also in the quadrupole approximation. So this is a quadrupole cross section of the same atom, which is mercury, and you have got a similar phenomenology governing the dynamics of photoionization in higher multipole approximation as well. Here the cross sections are extremely small. So this is like 10 to the minus 5, this is on a logarithmic scale. So this is 10 to the minus 5 megabarns, this is 10 to the minus 6, and these are extremely weak cross sections. So usually they cannot be detected, but their effects can be seen through other measurements like angular distributions of the photoelectrons. So it is nevertheless an important property to investigate. So now let me show you the result for mercury 4f, and in this case you have a local minimum over here, and it would be tempting to suspect that this is a Cooper minimum, but then it is not. The reason it is not a Cooper minimum is because your initial state is 4f, and from 4f you can have dipole in the dipole approximations transitions where delta L is either plus or minus 1 and delta J is plus or minus 1 or 0. Okay, so these are the dipole selection rules that we get from the Wigner-Eckart theorem, and using these selection rules you know that the initial state, which is 4f spin orbit doublet, so you have got 4f 7/2 and 4f 5/2, there are two levels, and then you can have transitions with under these selections rules either to G states or to D states, but then again to continuum G states, which will also be spin orbit split, right. So now you consider all channels from the initial spin orbit doublet to all possible final states which are also relativistically split, and consider all transitions which are possible within the dipole approximation. So it is not just a single channel anymore, but you have a number of channels. So you have 3 channels which go from F to G and another 3 from F to D. Now what happens is that the centrifugal barrier for the G waves is much larger. You know what centrifugal barrier is. In the hydrogen atom radial equation we had this term L into L plus 1 by R square, right. So that is the one which is referred to as the centrifugal barrier potential. It is a pseudo potential, it comes because of the reduction of the 3-dimensional problem to this 1-dimensional radial equation, but then it will have real effects, and this means that as a result of this centrifugal barrier, which is a repulsor potential, the continuum final states which will have a larger L, they will not be able to penetrate into the core, and I had discussed this also in the context of scattering, that the continuum states, if they have large angular momenta, they will not be able to penetrate into the core, but then the penetration will increase if the photoelectron energy or the photon energy will increase, right. So the cross section will be minimal at the threshold, but as you increase the energy at which photoionization is taking place, then the cross section in those channels will actually go up. So in the case of mercury 4f photoionization, you have the 4f to G photoionization, it increases from the threshold, whereas the photoionization from 4f to D waves, you know, that decreases monotonically, and the sum of the cross section is what you see from integrating the cross section in all of these 6 channels. So it starts dropping down from the cross section, goes to a minimum, and then rises again because the oscillator strength picks up in the other channel. So this is not a Cooper minimum, but then it has a similar behavior. So notice over here that the photoionization cross section is not monotonically decreasing, it monotonically decreases only beyond this, but there is a delayed maximum. This is because of the centrifugal barrier effect, and there is a local minimum which is coming because there is a competition between the oscillator strength in F to D channels and F to G channels. So, these are some very interesting details which one has to be concerned with, and we cannot apply these laws without additional considerations. So, let me now remind you the definition of the oscillator strength that we had in the classical model, and now we are using the quantum model in which we are considering explicit transitions from quantum state EI to a quantum state EF. So, in this case the quantum mechanical definition of the oscillator strength is now revised, and it is given in terms of this dipole matrix element. Okay, so, this is the definition of the quantum mechanical oscillator strength, and in as much as this classical oscillator strength definition gave you an integral of the oscillator strength over all the frequencies to be equal to 1, in the quantum mechanical definition you have this omega which is the difference between EF and EI. So, this can be either positive or negative depending on whether you are talking about absorption or emission, right. So, the oscillator strength can be either greater than 0 or less than 0, which allows for whether you are talking about absorption or emission. And similar to a sum rule over here, this is a sum rule that all of this oscillator strength when you integrate over all frequencies adds up to 1. So, the quantum mechanical oscillator strength also adds up to 1. This is known as the Thomas-Reiche-Kuhn sum rule, and we will derive this rule now. So, this is the definition of the oscillator strength, and this is for the position vector. Let me write the corresponding expression for a single component, one of the 3 components of the position vector like x. So, this is what this definition boils down to for the x component, and similarly there are corresponding expressions for the y component and the z component. Okay. Now, let me take the expression for the x component. This is the modulus square of this matrix element. So, I write this modulus square in this form, which is Ixf times its complex conjugate. Now, we already have an equivalence between the position form and the momentum form. So, using this form we can write these elements in momentum form. So, I have written the first of these elements in terms of the momentum operator. So, one is in terms of the momentum operator, the other is still in the terms of the position operator, and this is the process that we are talking about, that you have got 2 quantum states EI and EF, and you talk about the energy difference. But of course, the omega IF is equal to minus omega Fi because one energy is above the other. Okay. So, the 2 frequencies which are coming here, omega Fi and omega IF, so these have got opposite signs. So, they do, the numbers cancel each other, but they leave a minus sign that you must keep track of, and the m of course in the denominator cancels this m, and this is what you get for the oscillator strength. So, now you have this expression. The matrix element for this can also be written in terms of the momentum operator, and if you take into account the same relationship and the equivalence between the position and position form and the momentum form of the matrix element, you have this again omega IF and omega Fi over here. So, you will get again a minus 1 sign, and then the common factors like m cancel out, and then you are left with a rather simple expression. So, this has got a very similar form, but it is important to keep track of these details because you will see that it leads us to a very important result. So, this is the form that I would like you to keep track of. I am going to use it on the next slide, okay, and then I am also going to use this form which is completely equivalent to this. So, this is the last form that we got, and all I have done is to write this I in the numerator. So, now it becomes minus 2I over 3 h cross. Now, this is the form which I had on the previous slide, and both of these forms are completely equivalent, right. So, I can write the oscillator strength as half of what is over here plus half of what is over here, okay, because both are exactly the same. So before I do that, let me bring this minus I also to the top, and then I change the sign. So this is 2I over 3H cross, and now I can write the oscillator strength as half of this expression in this red loop and half of this expression in the red loop. So if I add these two pieces, add half of each of these pieces, I should get the oscillator strength. Now when you take half, the 2/3 will become 1/3 in both. So you get this 1/3, and this is the sum of these two terms, and this allows us to, this is the matrix element corresponding to a transition from I to F, but now I can sum over all the final states. So carry out a summation over all the final states, and this is a summation of over all the final states on the left hand side, also on the right hand side, and what you have on the right hand side, when you carry out a summation over all the final states, you get the unit operator over here, that is the resolution of unity. Okay. So the resolution of unity, when you consider all the final states, allows you to recognize that here you are taking the difference between these two terms, and the operator whose matrix element is under consideration is nothing but the commutator between position and momentum. Okay, it is xpx minus pxx minus xpx, and that is something that you know from the Heisenberg's principle of uncertainty, which is IH cross. So plug it in, and when you put this term over here, you find that all of these oscillator strengths, when you sum over all the final states, gives you 1/3, but that is only for the x component. You get a similar result for the y component and similar for the z component. So when you add the three pieces for the x, y and z, you find that there is a sum rule very similar to what you had seen in the classical case, and this is the Thomas-Reiche-Kuhn sum rule as it is called. Now it is rather exciting to observe that we arrived at the Thomas-Reiche-Kuhn rule using the uncertainty principle. Okay. So if you know the uncertainty principle, you can get the Thomas-Reiche-Kuhn rule. On the other hand, if you had reasons to believe that the sum rule should be correct, but did not know the uncertainty principle, and ask a question, what is it that will make the sum rule valid? The answer would be that position and momentum operators do not commute, and their commutator is actually equal to IH cross, right. This is in fact exactly how Heisenberg got it. Okay. Heisenberg was working with a large number of problems involving matrices and so on, and he was working with spectroscopic sum rules, and this was one of the inputs which led him into discovering the non-commutation between the position and momentum operators. So you will find a reference to this in Fano and Rao's book. So this is really very nice, and now let me go back to this definition of the oscillator strength in quantum mechanics. This is for one electron atom. For n electron atoms, you can sum over j going from 1 through n for all the electrons, because there will be a similar oscillator strength for each electron, and when you sum over these terms for all the n electrons, then you find that this summation will be equal to n, not equal to 1. So this is equal, if n is equal to 1, you get the Thomas-Reiche-Kuhn sum rule as we derived, but then for n electrons it will give you n, which is the number of electrons. So these are the sum rules, and notice that there is a 2m over h cross over here. So I can rewrite this sum rule, which is this, which is a summation of all of these terms, but if I write this sum rules without this 2m over h cross factor, so sum over f omega times the modulus square, right, this will obviously be equal to h cross over 2n. Okay. So you can write this as a sum over f of omega to the power 1 of the modulus square. It is the same thing. except that I am making all of us conscious of the fact that this is the first power of omega, and you can construct such summations for other powers of omega as well, like omega square, omega cube, omega to the power n, and there are several other sum rules which I will not go into details for this course, but there are a large number of sum rules. So we have got only the first one, which is the Thomas-Reiche-Kuhn sum rule, but there are other sum rules for other moments. So these are called as moments of the frequency. So for omega to the power 1 is what we have considered, but there are higher powers also that can be considered. So this is what we have got, that this is the expression for the transition rate. In the dipole approximation we arrived at some simple expressions. This is the dipole approximation, and in which e to the I k dot r is set equal to 1. You have got epsilon dot r, so there is a cosine term which is cos square omega, and now you have got e square in the numerator and the square of the matrix element of the position operator. Okay, that is the dipole. Okay, do you see that? Because you have got e square and d, so you can write this in terms of the square of the dipole operator, and this is possible because you approximated that e to the I k dot r equal to unity. So whenever you set e to the I k dot r equal to unity, and when are you going to do it? You will do it for large wavelengths, when r over lambda, e to the I k dot r, which is a power series in r over lambda, can be truncated at the leading term, which is equal to unity. Okay, so that is a low energy approximation. It is called as the dipole approximation for the reason that is now obvious to you. So this is why it is called as the dipole approximation, and you can certainly integrate this out over various angles. If you take the average of cos square gamma over all the different angles, then you get an expression. So you get a 1 over 3 for the dipole approximation for this transition rate, and this, just for the sake of completeness, I will show that these expressions correspond to what you might have learned as Einstein coefficients A and B. So those are directly related to this, because you would expect them to be related to the absorption and emission process. So you have got in the dipole approximation this transition rate per unit energy density. If rho is the energy density at frequency omega, then you have to divide this by rho, but the energy density is intensity over the speed of light. So you have got this I over c in the numerator as well as the denominator. So these terms will cancel each other, and you are left with this transition rate per unit energy density, and this is what corresponds, which is defined as Einstein's B coefficient. So this is the Einstein B coefficient for stimulated absorption from I to F. Then you have a similar term for the emission also, but then emission can be because of two processes, either spontaneous or stimulated, right. So for spontaneous emission, you have got a rate which depends on the number of atoms in the final state multiplied by a rate coefficient, which is the Einstein A coefficient. And then for the stimulated process, you will have the rate determined not just by this number, but also by the density of radiation field at that frequency, and another coefficient which is the third Einstein coefficient, which is BIF. So there are three Einstein coefficients to talk about, and these are the three coefficients, and then the rate at which the population will change is determined by the number of atoms per unit time, making the absorption transition from I to F, which will be given by this rate expression in the absorption. And now you have these expressions now both for absorption as well as emission, and if you have an equilibrium, then these two rates will be necessarily equal, right. So you just set them equal to each other, and you find that this ratio is given by the ratio of the populations, which is given by an exponential factor depending on the absolute temperature of the system, right. So this gives you an expression for the ratio of the two populations, and you can swap this equation, play with this and get the expression for the energy density at this frequency. What must this correspond to? It must correspond to the Planck's law, right. It must be the Planck's law, and this is the Planck's law. So now if you demand an equivalence between this expression and this expression, it is obvious that it will hold good if BIF is equal to BFI and AIF is equal to h cross omega cube over this factor times the B coefficient. So this is the relationship between the three Einstein coefficients. So with this I will conclude today's class. If there are any questions, I will be happy to take. Otherwise we will take it from here. We need one more class in which I will get the expression for the angular distribution of the photoelectrons.
This length form are equal.
Well, as long as you can make an approximation that the potential is a local potential, okay. So if you have a non-local potential, so in the Hartree-Fock you will not get equivalence between the length form and the velocity form. However, if you make a local density approximation to the Hartree-Fock, like the Slater exchange approximation or any local density potential, okay. So if you make a local density potential approximation to the Hartree-Fock exchange potential, then the effective potential will again become local, and that is required for the equivalence between the length form and the velocity form. So typically the equivalence hold goods for local density potentials or other potentials to which you make a local density approximation, but then there are some other situations also, like when you do many body theory. If you do a complete many body theory using the random phase approximation, for example, you do get an equivalence between the length form and the velocity form, but that is for a different reason. It is not because the potential is local, but it is for a different reason. So there are some other situations also. Any other question? Okay, so thank you.